All right, so we have begun. Everything comes through the way it's supposed to. So we are looking at this second one, and I'll take you as far in the interest of not having you here forever and a day, which hopefully you'll appreciate. I'll get because I can send you a lot of the rest. I figure we'll try to get out of here where I stopped more or less with the other group, so that you can get this one of the same presentations from before. I think it'll help make your lives a little bit easier. So moving on. This is really how bone becomes bone. It is so some of this is contextual things that are important. Effectively, with the exception of the skull and the clavicles, everything comes from a cartilaginous shell. So, and really, it's all about we begin to start to see bone as early as 2 months. This is really it's important stuff because a lot of times we'll be able to, oh heavens, let's say with a lost child that and you know abandoned child, maybe that we don't know the exact age. There are certain landmarks when things start to ossify. If remains are found, if skeletal remains, we can determine whether it's accidental. We can determine whether it's intentional, horribly so. We can identify ages. We can see if the bone is still growing. Is it a small adult? Is it a large child? And certain bones finish this process at certain times. So it's not all magically at the same time. So I years ago, it was a long time ago when I got board certified, you had to know all those dates and things like that. That's the kind of minutiae you have to remember for these very, very high level examinations. Okay. So now, believe me, you may seem it's fun, but this is what a lot of doctors and nurses do, and healthcare people do. You learn about a lot of this stuff. You can't hold it all in. It's almost impossible. You do what everybody else does. Just think, you look it up. Stuff that you do every day, you don't want to look up. Meds you use every day, techniques you do every day, you learn those. They're ingrained. When you see somebody with a diagnosis you're unfamiliar with, and what do I have to do in my job to make their lives better? You look it up. What do I have to watch out for? What are they taking? That kind of stuff. That's the way you do it when you're doing things properly. So, again, it starts early on, and it basically, when they say early adulthood, our bones stop growing in general. Again, for boys, it can be a little later, 18 to 21. There's a lot of boys that have had adult growth spurts, particularly during the college years. And girls, 16 to 18, I think it's more on the 16 than the 18 side. Everybody's different. This is my maximum height when I was in ninth grade. It just stopped there. For whatever reason, it stopped there. And I mean, I had other relatives in my family on my dad's side. They grew. We were the same height, and magically they kept growing. I had 2 male cousins, one who's unfortunately no longer with us. They were both 6'3" plus. Just the way I didn't get that genetic packet from my dad's side. Just didn't. So all of that's part of it. So we see, and we'll be looking at when they have growth spurts. And you're all familiar. Typically, they start. Usually, there's one pre-adolescent, and there's a big one when it's at puberty, because really the triggering factors, particularly things like estrogen in women and testosterone in men, really trigger that. And interestingly, when you get even higher levels, it actually makes it close. I mean, so that's what we don't really understand the dynamic as well, but we know that increase in those levels at a certain point in time, for whatever reason, stops it. Doesn't mean it stays at a high level, it just stops at that particular level. So the chemical controls are understood a little bit. And again, the bone is constantly, it's just no longer there. Don't fall in love with your bone today, it's going to be gone tomorrow. So the famous name for this is endochondral or enchondral. They're both the same thing. It means in cartilage. Ossification means we make bone. So we're making bone out of cartilage. Replaces the hyaline cartilage. That intramembranous bone, other than knowing what it is and how it presents itself, there's really not a lot that you need to know about It's just different. The big thing to know about it, I already said, and I'll just say it again so you know it's going to be there. Something's coming your way down the road. You have cortical bone on the outside, cancellous bone on the inside. It's like a sandwich. And again, it's very limited. Skull bones, clavicles, that's it. Flat bones pretty much by definition. Everything else, cartilaginous shell, vast majority. So they're going to be, they aren't all magically bone at week 8. That's kind of when we start to see these processes. And we really can identify. We made it a lot easier is having ultrasounds. We never really had them. That's a relatively recent luxury. People will do gender reveals and things like that, like they did with my great grandson and my other grandkids, other than like the first one. So all bones, as you can see, with those exceptions, it really starts the second month of development. Hyaline cartilage models, and this is where it gets a little wordy by this text. And I think it's more information than you really need to know that are there. Effectively, where that nutrient artery comes in, which is really important, that's really the location of what we call the primary or first or main ossification center. You're going to see it's in the shaft. So we start in the shaft. The diaphysis is the name for shaft. And secondarily, an independent blood supply goes into the epiphyses, the ends, if you want to call it that. That's fine. Fancy name is epiphyses. And what they do, as soon as that blood comes in, it's like a magical change. It changes what was the sheath that we call perichondrium, and all of a sudden it changes in those cartilage cells become bone cells, and it goes from perichondrium to periosteum. You'll see this. These steps are not terribly vital. All of this stuff, it's easier to look at it diagrammatically. I went through explaining those before, and I don't think it was very beneficial to previous classes. So here you get, this is before birth. By birth, we're already here. Okay, by birth, we've already started to get bone going in early on. First thing we see, what is this quote unquote bone collar? I don't know. So you don't know. We know this is cartilage. Okay, what's this ossification center? Same thing. And then, somewhere between that and the third month and another, 3 to 4 week span, now we finally get that initial blood vessel, and that's going to become the nutrient blood vessel, the main blood supply to the bone. And by that time, it's been effectively what it's done. It's changed that lining on the exterior to periosteum. We've already started to create bone on the inside, circulatory pattern, even though the vast majority of this is still cartilage. Now, by the time birth rolls around for most of these, the mid-shaft area, the diaphysis area, is starting to be bone. You're getting cortical bone, as you would typically have in the shaft on the outside, compact or cortical. You have spongy in the middle, and the blood vessels throughout it. And now, right around the time of birth, what we call the secondary centers, the separate blood supply to the ends, the epiphyses, the head and the base, proximal and distal, whatever, head and the condyles and the femur, whatever you remember. Works like that. And then varying over time when these things appear and we can actually identify them, and when they close from that part of childhood through adolescence, effectively, sort of until puberty, and we start to see later changes, so to speak. Now we begin to see the true development. We see a bone with a shaft. We see separate blood supplies in the epiphyses. The shaft is the diaphyses again. And you see the growth or epiphyseal plates. That, ladies and gentlemen, is the structural weak point of growing bone. If bone is going to be damaged, that's where it's damaged. Inevitably, when we see a fracture in a growing bone, and I treat tons of kids' fractures, that's typically where it is. A lot of times you don't even see it because, as you'll see very shortly, the plate almost looks like a fracture. It's almost like it snaps out and snaps back in. So a lot of times, and you'll find this to be true if it's happened to you, or maybe it'll happen to your kids, or be an area where you're working in, where we typically wait 10 to 14 days for a second set of x-rays to look for the signs of healing. That tells you there's a fracture. Sometimes the fracture becomes better defined because the cells gobble up the broken bones, the little microscopic broken bone, and you can see fracture there. There's certain x-rays in bone. In the study, when we look at how bone heals, we look at the initial, that probably 10 to 14 day x-ray in the 2 month. It's a really important x-ray. I mean, by that time, we should have significant healing. And, barring the unforeseen, we shouldn't have to have a whole lot of, maybe we can just go into rehabbing it and exercising, increasing activity. Here's the intramembranous one. I can't say a whole lot about it. Mesenchymal, again, is those magical cells that can be fibrous or cartilage or bone. They're the ones that it forms. I don't care. This is basically, and you saw that illustration before, at least a couple of times already, where you saw that flat bone, one of the bones in the skull, and effectively cortical on the outside, relatively thin, not super thin, but relatively thin, and a marrow cavity, and cancellous bone. That was the flat bone, classic flat bone. And so again, the same two terms you saw associated with cartilage at the start of that last PowerPoint sequence: interstitial for elongation, appositional for shape. And what happens is as long as the growth plate is present, it will continue to elongate. Once that disappears, and again, that's under chemical controls and hereditarily based and all production of a variety of factors, hard to predict. You'll learn, if you have kids, they do those charts where they'll measure the baby's weight and the baby's length. And basically there's a series of charts that tell you what percentile they're in. In parenting, they tell you, if you take, when the baby was born, or like how long the baby is at age 2, double it, that's how long they're going to be as an adult, that kind of thing. I don't know if that's true. People will tell you that. When they should go so many inches and things like that. What pediatricians do, or people who are nurse practitioners in pediatrics, you use those and you put them on a table. And basically it tells you what percentile of the growth they're in. Children who are in that like 25th percentile after a certain period of time are too diminutive, and we have the availability of using it. They're not producing and releasing enough human growth hormone. It used to be really tricky. Now we make it genetically. And I can't even tell you how many students I've had over the years who had treatments because they were probably going to be about 4'8". One gal early, and oh heaven, it's like the second class I taught here, third. I taught here the third. It's a good 15, 16 years ago. And she was telling me about it. She happened to go to the same school where my wife's kids go, in Seneca Valley, that area. So it's a little unusual. Back when my kids were little, that's the kind of thing that they send you down here to Children's Hospital, had specialists look at it because they had to make a big determination. Very expensive treatment. So, and again, bones stop growing and they just continue to shape. Face is interesting. It's an interesting thing. If you remember anything I'm telling you today, and maybe it'll join you, maybe 10 or 15 years from now, you'll pull out the old high school yearbook and look at people, and maybe you've seen one of them recently. Look at their faces then compared to what you've just seen. Yeah, sometimes they look just the same, and other times they look very much different. So it really is. So there can be some additional. Certainly, some of them are not so subtle. Most of them are pretty subtle. Okay. I keep telling myself I look that way. My wife tells me I'm just full of it. We don't see ourselves in the mirror as well as much as others see us. It's another one of those neat, like Disney, mirror, mirror on the wall, that thing. Right? Sleeping Beauty, right? Was that? Well, yeah. Is that Sleeping Beauty or was that snow. No help here. I'll have to look that up. It's a whole. Really, they're weird. I mean, gals, is your mom letting you go in the woods with 7 short guys? Live there? I don't think so. Come on. One of them's named Doc. What the heck's going on? And, I mean, we're politically incorrect. Are they really dwarves? The whole thing? Sketchy. I'm going to live with 7 dwarves in the woods. Sure, yeah. Tell me about it. That sounds weird. It's kind of a one-gal commune. I don't know. Makes you wonder, those Disney people. My kids are still getting over that witch in the water and the Little Mermaid. Ah! No, actually not. For my kids, it was more of like when they first saw 101 Dalmatians. So what happens, the beauty of this area where the bone grows, and this is an important part to remember. So here you have it. So here you have, these are the epiphyseal plate areas. What's left of the cartilage, you'll learn in joints, is at the ends where it forms, and bones forms joints. This is the shaft area. The bone grows in such a way that the cartilage increases in this direction, and effectively the growth plate gets pushed away. Cartilage goes toward the center or goes toward the shaft, and the growth plate gets farther away. So, I mean, so we've got a longer bone like this now, and effectively, the cartilage is now way down here and way up here, and we've effectively elongated the shaft, even though I'm probably not drawing it very well. Okay, the epiphyseal plate, until it closes, stays the same. So, and that's what they call the so-called resting. You don't have to know the names. The one name you do have to know is where it weakens. So what happens is the cartilage starts to grow. And it begins to grow because things are fed by blood supply. The blood supply for anything is where? It's here in the middle. This is where the blood supply is. So the cartilage is going to start to grow in this direction. The trouble is, it's a two-edged sword, because even though it grows, the blood is eventually going to destroy it. It's going to damage it. When cartilage starts to grow and enlarge, exposing itself to elements of the blood supply, it begins to die. Simple as that. So it proliferates, and then, as you'll see in the actual slides as well as the drawing, it begins to grow and enlarge. At that point, it's starting to deteriorate. And biologically, what happens to things in your body when it deteriorates? They calcify. You're taking a routine chest x-ray of somebody as a pre-op, and all of a sudden the radiologist looks at it and sees the blood vessels in the heart, the coronary arteries are calcified. They see this little flecks of calcification. They're in trouble. By that time, again, that blood vessel is probably 75% gone. You're never going to get rid of those. The calcification is always there. They're permanently damaged. Does it mean they're going to have a heart attack and die? Not necessarily. But we have damage that's tangible, observed. Calcium goes to things that are dying or severely damaged all the time. It's got a fancy name. It's called dystrophic, dystrophic calcification. Don't have to know that. But dystrophic means not growing properly, which could mean damage, not healing properly, etc. The zone of calcified cartilage, or calcification zone, is the name you must remember. That is within the epiphyseal plate. That is the layer that is the true structural weak point. It's in that layer where fractures occur. Consistent. Not only do we know it's the growth plate, we know the area of it. Because effectively, that's the transition. Here, they're growing. Here, they're enlarging. Here, effectively, they're dying or have died. Because once they've died, they're going to become bone. So proliferation, and it's always on what they call the diaphyseal side. That's where it's dividing, heading toward the center. So effectively, the new cells formed kind of lay on top, and they're pushing it farther away. It pushes the older cells closer to the middle, closer to the blood supply. They begin to enlarge, erode. All that's bad. Stop being complete little spaces formed between them. And then it begins to calcify. They die and they deteriorate. That's why it's a weak point. It's no, I mean, dead tissue has lost its structural integrity, much easier to damage from trauma. And then it starts to ossify. And I mean, it goes through all these processes, and it's going to be spongy bone. So you don't have to worry too much about that. This is interesting. First of all, we will probably look more at x-rays next time than this time. X-rays, when we do the fracture, we'll look pretty closely at them. The x-rays, okay, why is that not a fracture? Okay, because if you can see, it's typically growth plates are smooth areas here and here. You can see one over here. This is distal femur, this is proximal tibia. If a child came and I fell, but only my right knee hurts, and you saw that on the right knee, how would you know it wasn't a fracture? Typically, we were taught with children, I do not know if they still do it today, to x-ray both sides. Because we would compare the growth plate on the unaffected side, let's say the left, to the right. And if we saw an irregularity here, all of a sudden there was a little notch on one, it just didn't look quite right, that might indicate that there had been some damage there. Again, not having practiced or done this for a quarter of a century, who knows how it's changed. Understand, it's unlike what you see on TV. I mean, they do a very good job. I rave about that show on HBO Max that they're filming here in Pittsburgh called The Pit. It's nothing but great. It's just a fabulous show. You're not going to MRI and CT everybody who comes in the emergency room. You can't, financially, you can't do it. If it's a major trauma center, you're getting major trauma cases. Okay, go do that. But a little kid comes in, like sitting in their ER there, in the emergency room there, you're just not going to do that. We call it overutilization. You're ordering $1,000, multi-$1,000 tests on somebody who probably could just put a cast on and be done with it. And if that doesn't make it better, then you can order more tests. So there's, understand, many of you, if you're going into those kinds of fields, get the idea of what happens and what doesn't. We're not doing, not everything is how it's done at a level 1 trauma center. I worked in a very nuts and bolts ER for 2 years. You can do a lot of stuff, but the complex stuff, you got those patients out, you get them in an ambulance and send them to a specialty hospital. We were in Philadelphia. Kids went to Children's Hospital of Philadelphia. We had major trauma centers. We sent them there. Burn units, different places. So here, this is the actual photomicrograph. That's what it looks like microscopically. Normal cartilage. You can see they're still growing here, fine. But here, as they're getting pushed closer to the blood supply and the plate is going farther away, they're enlarging. The deterioration is here, okay? And now they begin to calcify, and that makes the transition. So the calcification zone, or zone of calcified cartilage, weak point. And here's just a demonstration. Now we're starting to get into bone. So it stops, it begins to slow down, and eventually closes. Why does that happen? Okay, we know the aging. It has to do with chemical controls. There are different chemicals, and you'll see they'll go over them for you, impact that, as you will see. The oddity, there's just a lot of cases, and I always tell the anecdotally, meaning there's a case that really shows you how boys can grow. A very famous basketball player won an NBA championship, 88 or 89, and he was on the first San Antonio Spurs championship team. They were in 5 in that run. His name was David Robbins. He was from the Naval Academy. He entered the academy as a 6'4" point guard. After his first year, he was a 7'1" center. He grew like 9 inches his first year. Called him the Admiral. He only served, I think he graduated 82, 84, maybe 82. And then Pitt picked up the head coach from that team. Then he only served 2 years. It's a 4-year hitch if you're in a service academy. He only did 2 years because, I mean, sailors, you can't, if you're on a ship, or if you're on a submarine, you can't be taller than like 6'4", 6'5". You can't, it's too small. Ships all have hatches you walk through. They don't have doors. If they have a door, they're up on, it's a door to the bridge. Right? Everything has to be watertight. And so you run through a hatch, and then if you didn't know, you have to seal the hatch behind you to keep it all compartmentalized, watertight. You get yelled at a lot if you don't do that. I know. My son yelled at me. I'm bragging. He was the captain of a destroyer. Believe me, I know my way around these things. Okay? So they sent him home in 2 years, and all of a sudden, he becomes a star basketball player. So this is not unusual. And you'll know relatives, you'll know friends, and they come back, what happened to you? You're 5 inches taller. They shot up. You very rarely see that in girls. Sometimes people say, oh, my shoe size is changing, I'm growing. As an adult, that's more about this appositional growth. It's maybe shape changes. A lot of times the soft tissues are weakening and things are beginning to spread out, particularly in the feet. When they spread, sometimes they'll elongate. So sometimes the shoe will be wider, sometimes it'll be longer. We'll have to wear a bigger shoe size to accommodate your foot. I mean, I'm with mine, nothing in mine has changed. So again, the growing bones throughout life, they thicken in response to stressors, different things. If you're depending on your occupation, how big you are, how small you are, whether you are doing a lot of lifting, is it upper extremity, whether you go to the gym every day, it all depends. And so it's something that's a natural process. So effectively what happens, to maintain the whole idea of this particular slide, is we sort of conserve the bone. We move it around. We make it thick enough where the pressure is to absorb that, and thin enough that it can bend a little bit without giving way. So you're trying, basically the amount of bone to some extent stays conserved. And if all of a sudden your job changes, your life changes in some way, shape, or form, all of a sudden you decide to go on a workout binge to lose weight or to get in shape, or you go in the other direction because you're tired of it. Whatever, all those things play a role. It's kind of showing you. So this bone, effectively, let's say this is what will happen in a bone that's growing. Here's the original contour. Here's the grown contour after growth and remodeling. So you can almost trace it back and see what's happened. And so it didn't make the bone any weaker. You just redistribute it. Particularly where that cancellous bone was, where the cortical bone was, where all those weight-bearing pillars were. And now we get to the chemicals part of it. And then we'll get to how the calcium, what role it plays in that. And then we're getting pretty close to the end of this whole thing. Okay, hormonal regulation. Surely in growing bone, growth hormone. Growth hormone is with us all the time. Whenever our body wants to increase mitosis, whenever we're doing healing, this is all endocrine. You're going to get this separately in AP2 with endocrine. We release growth hormone. Again, we can make it now artificially, and not artificially. We effectively make it genetically in the lab. It's effectively a GMO, a genetically modified organism, the way we make insulin. So growth hormone's been around for a while to do this with. So it's available for people to use, like I said, for people where there's concern to be very short of stature. And surely in growing bone is the most important. So it stimulates that activity, infancy and childhood. It's thyroid hormone. This is not its only role. Thyroid hormone is important in every metabolic function in your body. It governs how rapidly or how slowly you do things. It's very much involved in everything, whether it's reproduction, whether it's kidney function, whether it's cardiac function. All of these, when you see an endocrine, you'll go over it, thyroid, and it'll show you what role it plays. Each one of these systems, you'll be amazed. So effectively, and so it's interesting, the thyroid is a gland, if we had to, we could do without, because we've been making thyroid hormone for years. Okay, we've had people on thyroid supplements for years, and we even make agents if their thyroid is going too fast. So it's very fascinating in that regard. Thyroid, the best analogy is it's like a car. It's like if a car is really in good shape and you turn it on, it just purrs. You don't hear anything. If the car is old and not maintained, I mean, hypothyroid, you turn it on, it sputters, it can hardly start. And on the other hand, if it's hyperthyroid, you start it, it's just like the engine goes crazy, revs. Like my boys were into, like most boys in their particular age group, were into car. Gas was cheap. Muscle cars, 8-cylinder engines, racing and stuff. They all did that. I used to joke with boys, it was cars and girls. With my daughter, it was boys and clothes, all not necessarily in the same order. So that plays a role. So modulate's a very good word, proper proportion, so it's not excessive growth. And you'll see and when you get into endocrine, you'll learn a lot about growth hormone. What happens if the bones are effectively, you can cause giantism or different kinds of dwarfism. If it's before the growth plates close, and there's a real oddball condition generally from pituitary tumors that you'll learn about called acromegaly, which is really changes somebody facially. It's a weird. You don't see a lot of that coming out. You'll learn about that in endocrine. Not for us. So the big players when it comes to adolescent, the puberty-based growth spurts, and also in bringing along the end of growth, testosterone in males, estrogen in females. And so again, whatever the signal is, they play a role in ending the growth and by closing the growth plates. And again, there's any of these things can cause irregularities. So we understand the chemical basis fairly well about those types of things. And here's the numbers. 5 to 10% of all of your bone mass every year recycled. So if you do the numbers, cancellous bone, spongy, every 3 to 4 years, all of it. Cortical bone, every 10 years. So the original equipment surprisingly is not there. And again, the vast majority of your body, other than your nervous system, brain, spinal cord, nervous system elements, heart, skeletal muscle, smooth muscle, all changed over. So again, we look the internal surface is where we begin to see this. And all of these, it's all about stressors. And it's little signals to the osteocytes, whether they're electrical signals, which could very well be. The flow of materials creates electrical currents. And they play a really pivotal role sometimes, everywhere, as well as the chemical signals. And what happens, it'll tell some cells, okay, we're under a lot of stress here. We have to build or thicken the bone. Or the flip side of that, we have to thin it out. So what's the magic of how we get rid of extra bone? It's these guys. It's called the osteoclasts. Again, whenever you see the term places, it implies breaking apart. And this is where, and they work effectively. These are similar to the way macrophages work. We talked about them in the cell, the enzymes for digestion and defense. This giant cell with multiple nuclei and multiple organelles is filled with these chemicals. At a signal, and you'll see the signal comes from something you're going to see in a second called parathyroid hormone. It releases those enzymes and it releases acid proteins. And in that environment, it breaks apart. And this is the idea of osteoporosis. It's not just loss of calcium salts. It's loss of the entirety of bone. This combination breaks apart the osteoid, the organic portion of bone, and as well as breaks apart the calcium salts, the inorganic portion of bone. The inorganic portion is, and all of these things get absorbed into the bloodstream, reutilized by the bone as a scientific converters. And this is how we get calcium when necessary into the bloodstream. So they play a pivotal role in calcium regulation. The next topic. End products, dissolved minerals, go across this cell, they gobble up debris, And as you can see, when they're done, they disappear. Apoptosis. The cells it's effectively as a unit that's used one time, and then we just make more. Just underscores what we continue to do is we remake the equipment, remake the cells. So everything is somewhat transient in its nature. You want to think this way. You remember they have those ruffled borders, depressions. They break things down to that surface. I don't do that. Thank God. And down the road, well, how does this magical stuff, the organic stuff called osteoid, how does it bind calcium? Okay, it basically has a chemical called alk-phos or alkaline phosphatase. When we see irregularities, a lot of tissues have this chemical. Bone has it, liver has it. Down the road, you'll probably learn what's in regular blood tests. There's something, you may have heard of it, called a BMP, Basic Metabolic Panel. It's a quick snapshot of about 18 to 24 tests, depending on the lab, your sugar, your electrolytes. Alk-phos, what we call it, is in that tool. BUN creatinine. So that, and interestingly enough, when we see irregularities in that, one of the first things you think about is bone. The other thing you may think about is liver. You know, you get an idea what normals and certain patterns are with that. That's not something I'm going to ask you about, but because the name is highlighted, I think you should be familiar. I think it's just back of your mind. And again, what happens is the calcium and phosphate ions, which are basically involved in that process, and that again, they form this very specific pattern called hydroxyapatite, particularly the calcium phosphate. You must be familiar. And so now we look at the hormonal controls. This is the whole thing about basically bone being calcium warehouse. And I can't make it strong enough point. There are three basic hormones that are involved. One, and the most important, the one is that basically is activated first. And remember, this is all negative feedback. Calcium has to be strictly controlled. It's important in everything. Blood clotting, how nerves work, how the heart works, how the kidney work, everywhere. If there's not enough or too much, we immediately address it. So let's say there's not enough in the bloodstream. We release something called the parathyroid, which is a different gland. Go next to the parathyroid, we release something called parathyroid hormone. You can always label it PTH, that's an acceptable abbreviation. It works in three areas. And what it does, this is all calcium osmosis metabolism. And the whole idea of parathyroid hormone is it works on bone, it works in gastrointestinal tract, and it works in the kidney. In all of those areas, it begins basically to work on bone, to begin to break it down, and in doing so, it increases the level of calcium in the bloodstream. It works along with, and it must have both of them, in the gut with vitamin D. And in doing so, you absorb more calcium, and therefore, guess what? More calcium in the bloodstream. And yet, a third thing that it does, parathyroid hormone does, well, these two, is it affects the kidney and tells the kidney, hold on, don't urinate out, hold on to calcium. And what does that do again? Increases the level of blood calcium concentration. All of them raise the calcium. And with negative feedback, as soon as it starts to do that, it starts to raise it, it sends a signal to the parathyroid and go, whoa, you're good. Subtle. Remember, it's a set point. We make subtle changes to keep bringing it back to the set point. If it goes too low, it goes too high. If it goes too high, one of the things that activate mostly, there's some controversy. It's another hormone. That's why the thyroid is also not vital to us. It's made in the thyroid. This is an important role in children. What is called calcitonin. And what it does is effectively it puts calcium back in bone. So with excess, this probably plays a role in children, and in growing bone, really important. And so therefore, when it's out of the bloodstream, it lowers calcium levels in the bloodstream. And undoubtedly, you're going to revisit this, particularly in endocrinology. You probably revisit this in other chapters as well, which tells you how important it is. And so there's a lot of things. When they talk about mechanical, mechanical might be activities. Gravitational, I mean, gravity is a force. So if you had somebody who was in the International Space Station for 6 months, and when they got back to Earth, their bones hadn't been subject to gravity, it's been weightless, they would have atrophied. You would have not, the bones effectively would be to a certain degree osteoporotic, because it's unlikely that it would be permanent, but I'm sure there's a protocol. How do I hear this? I'm sure there's a protocol for when they bring somebody back, how aggressively or unaggressively let them resume their activities. Their bones probably couldn't take it. Oh, I got to get back into shape. Well, I don't want you to go out and run 5 miles tomorrow. You probably, something bad's going to happen to you. I don't know. This is my speculation. So calcium everywhere. Nerves can't fire. When we finish the joints, which is next week. After that, the rest of the class is all muscles and nerves, and it's very complicated, and calcium is the pivot point. Nerves don't fire without calcium. Muscles don't fire without calcium. It's a very complicated process. Calcium is all over the place, all the time. Our bones, that's about 3 pounds, by the way, if you do the conversion. Okay, 99%, about 3 pounds of calcium is found in our bones. Most of our weight comes from our muscle, not from our bones. Because even if you picked up the bones in the lab like that, there's a reason they're not, but they're not as heavy as one would think. Intestinal absorption of calcium, vitamin D is a must. They have to work together. We will not cover today. At the very end of this chapter, we talk about bone diseases. And the one that all of us essentially have is osteoporosis. Would it be fair to say 75 to 80% of all the people get osteoporosis? Yeah. And some are much more predisposed than others, much more common in women than in men. And as we'll find out, the treatment for a lot of this, the best time to treat this is now. I'm going to remake this point in spades next week. Got to start treating it now to avoid it. Sometimes it's unavoidable. There's a lot of factors involved. One of the things that we recommend, the kind of calcium, in the old days we used to call it Oscal for oyster shell calcium, calcium carbonate. A lot of people pop a couple of Tums every day, not so much for their stomach, for indigestion, for calcium. A lot of people take calcium supplements with vitamin D, Caltrate with vitamin E. That calcium is called calcium carbonate. That's less likely to form kidney stones. Excessive calcium can predispose you to kidney stones. We've seen a real uptake because of people taking the wrong calcium, particularly younger women, of kidney stones at an early age, which is usually was pretty much men, much more so. Men more prone to it with urinary tract problems. You didn't see it quite as much as men and women as men. It's kind of flipped a little bit. So a lot of times, and I'm telling you that if my advice, and it's strictly advice, from somebody who's no longer licensed, my suggestion, because I do it too, is to take a vitamin D supplement. You want your vitamin D, you can go too much. You want it to be at high levels, a little higher than normal, not ridiculously so. Calcium is a good thing to take along with it. I'll say, I say the same thing. I've told my daughter the same thing, my granddaughter the same thing. My wife and I both take it. We do it with there are a lot of good supplements out there. Here's the parathyroid. It stimulates those osteoclasts directly. Calcium raises, stops, again, it reverses. Calcitonin, the oddball, made in the thyroid. And this is where effects are negligible, but at high pharmacological doses, it can lower blood calcium temporarily. That's short for Again, whenever you see permissive terms like, it can, that means not it does, but it can. We don't know. There's been a lot of experimentation and looking into it to find a medicine that could treat osteoporosis. Anything that's been used to treat osteoporosis has had a variety of side effects, and they've not been particularly successful. This is one of the ones. In growing bone, clearly it plays a role. Whoever made this PowerPoint likes to think. I don't do those. And this just gives you an idea. It depends on the system. You don't broad brushes where low calcium and high calcium do this. Not a good thing. That's poorly written. But here, high calcium levels, this is what happens. If tissue is damaged, it calcifies. If calcium levels are excessively high, it even deposits calcium in healthy tissue. Seen that? Again, and so in tissue that's damaged, like blood vessels get damaged a lot, just routinely. Kidneys under a lot of stress constantly. And again, the stones, really significant. The calcitonin, again, I don't know. There's other things. Vitamin D can actually assist with osteoclastic. Again, I think it's very useful. Corticoids, say glucocorticoids, that's something you'll learn about in endocrine. If somebody, you got to be careful. I used to give people a lot of cortisone shots. That's not anabolics. That's not a performance-enhancing drug, steroid. That's grandma's knees acting up, and she got to cut a shot of cortisone. Get tendonitis, arthritis. A lot of times you got to watch out because that can do damage to those tissues. You can leach calcium out of them. We've seen that. So, I mean, really, you typically, most orthopedists probably 3 or maybe a shot every 3 months. Oh, my knee's killing me. Can I come back every 3 weeks? No. Because you're going to have doing damage. That's part of it. And here, Wolff's Law, there it is for you. Any stress they encounter, weight bears on them, the muscles pull on them. That's what made all those trochanters and tuberosities and tubercles, and epicondyles and foramina, blah, 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 blah. They grow or remodel into those responses. Stresses are always, not typically, they're almost invariably off-center. And the hip is the best example. And the shaft will thicken where it's bending. That's where it's got to reinforce itself because that's the major stress point. And that's if it's going to rupture with a stress fracture, that's where it's going to rupture. Where most of the stress is, and that's where they're going to try to make cortical or cortical bone or compact bone thicker. And again, we'll thin it out on the other side to sort of cancel it out. Here's the perfect example. If you look at this, if you took a radiograph of this, an x-ray, it would be thick here. It would be thinner, not thin, but thinner here. This would allow it to distribute the weight, and this would allow it to bend. Because imagine, your whole torso is sitting on these two guys, the head and neck of the femur. So when somebody breaks the hip, when grandma or grandpa falls down, breaks the hip, they didn't do that. The hip gave way. It's called a pathological fracture. That's what we'll study next time. Pathological fracture means the bone has weakened for whatever reason. Mostly osteoporosis, a tumor, could be something else. I mean, the vast majority are osteoporosis. For you folks, young people, most of the time when you have damage to bones and they break, it's an accident. It's a sports injury. You're young, you're active, you do stuff like that. So, I mean, I had a disc bulge when I was, how old was it? About 12 years ago. It wasn't that terribly old, but I had enough arthritis and enough resultant osteoporosis from that in my back for it to give way. And whether the disc gave way or the bone gave way, I think the bone gave way first. And oh boy. Everything's then I've been going to my chiropractor every 2 weeks. So you see it where it's here. And I'm trying to give you an idea. So typically when hips break, they break either in the neck is where it weakens or along here between the trochanters. So this is inevitably along this inner portion. So right-handed or left-handed, your right side would be thicker and stronger. Curved bones, thickest where they're most likely to buckle. That was the femur. Underneath, and this is what we look for stress fractures. in athletes, where we start to see the trabecular bone, a little under the thick cortical bone, the cancellous bone we look for. When we see that area start to thicken, that's usually a stress point. And again, weightlifters, power lifters, some of those bones you saw in there, you could see the difference between how distinctive some of the markings were and versus how limited they were in some of those. And again, if we don't use them, they atrophy. So, and this is the idea of the fluid. When the bone is being remodeled, or even when we're using the bone or it's growing, we see this. Back in the 60s, and I did this, we became acquainted because we were in Philadelphia. At the Hospital University of Pennsylvania, they came up with something called electronic bone healing. We would take a cast or a removable splint, would have electrical plates in it. You'd put it around a fracture, particularly one that wasn't healing as well as expected, like the 2-month x-ray looked bad. And basically, because they're charged particles, and you'd have 2 plates that would create a balance of charge in around a direction of charge. And basically, they had a plug coming out, and they plugged themselves in 8 to 12 hours. So when you're watching TV and you're going to bed, plug it in. And then you could take it out if it was removable, or sometimes it's incorporated right in the cast. I do not know if it's still used today. I haven't worked in a hospital or treated patients' fractures in 25 years. So I don't know if it's still a problem, but this was the idea was here. Detect the electrical current, or release chemical messengers that promote formation of additional bone. That was the science behind it. So hormonal controls tell you where and how much. Mechanical stressors play a role in that as well. And then we're done here with fractures as the last unit. So I'm not going to start that now. Fractures you're going to learn are interruptions in the overall integrity of the bone. I'm going to do this presentation a lot. I will probably send you a copy of it, and then we can amplify it a little bit when we see each other next time. Thank you. We're good. Bye-bye.